Hello everyone, and thanks for joining us. Today we are going to start a Compass lecture series on an introduction to complex dynamics. Our speaker for today's talk is Sukanta Das, a Ph.D. student at IIT Bhubaneswar, who will be talking on an invitation to complex dynamics, iterating functions in the complex plane. Sukanta, over to you.
Okay, thank you, Abhishek. So first of all, I thank the organizers for giving me this opportunity to present this subject here. So like this subject is not widely known overall this country. So that is why I put my title like an invitation to complex dynamics, iterating functions in the complex plane. So today's talk will be very much basic, and I will not go in deep. Maybe in the next consecutive talks, theoretical things what I'll prove. So first of all, okay, just 1 minute. Pen. Okay, so what this subject complex dynamics is all about. So complex dynamics is basically the study of iteration of analytic functions in C hat or C or B. So this basically comes from the uniformization theorem of simply connected Riemann surfaces. As we know that if S is a simply connected Riemann surface, then it is conformally equivalent to one of the following. That is, it is either C hat or C or D. So, but this case, yeah.
So, complex dynamics is only consist of the iteration of, or it also consists of continuous dynamics part. That's the instead of doing the dynamics on the discrete time. If somebody sees the if somebody studies the dynamics on continuous time, considering a differential holomorphic differential. So that's also the part of complex dynamics, right? So the statement complex dynamics
is
only study of the iteration of analytic map on C or some Riemann surface.
No. Like this is it's like this is not the analytic functions only. So it has some generalizations also. So here
no,
I'll be sticking with this.
I'm not talking about the generalization of the functions. I am talking about the generalization of iterating time. Here the iterating time is, you are mentioning what seems that f square f cube, that means the time is this number. But instead of considering the discrete time, you can also consider the continuous time by considering a holomorphic differential equation by dx dt is equal to f of x of t, where t is in complex number. So, but then that will be there will be also study of the dynamics, but instead of doing it discrete time, it can also be seen as a continuous time. But I think that also be a part of complex dynamics. So my point is that complex dynamics is only study of the iteration. Is this fully correct, or their complex dynamics also consists of some other parts? Actually, one of the part is some study of iteration. Oh, that's fine. Is it correct? Yeah, that's what I want to talk.
Yeah, so the point you have mentioned, so that is not I'm like erring off. So the thing is that so the study basically begin with the iteration of these functions. So that thing maybe is there. So I'm not aware of that thing. What you are saying, like continuous case, what you are saying, not discrete.
Okay. No.
Yeah.
Point is complex dynamics, I think, also consists of those things also, and not only the iteration of function. That's what my point.
Yeah. Maybe correct. Maybe you're correct.
That's something.
Yeah.
Just one comment on the question. So, yeah, just one comment on the question. I think it is related to like what he's talking about, I think it is related to something about loaner differential equation.
Yeah, loaner different, not even loaner. You just only when you just you don't have to go to the loaner thing. Just consider the dx dt is equal to f of x of t, where f is a
Yeah, but
holomorphic vector field.
yeah,
Sorry,
yeah.
holomorphic map you can instead of take on C, and then study the behavior of the solution in continuous time. You can see that whether the integral curve converges to a fixed point or it diverges, or you can study the semi group also on unit disk.
Yeah, exactly.
They are also that also part of the complex dynamics. So that's what
Yeah,
my point, that complex dynamics is only the study of iteration. That's has some flaw in that statement.
yeah, yeah, yeah.
Yeah, yeah.
Okay.
This is just a
So yeah,
small remark.
yeah. Yeah. So yeah, so that thing, like yes, I have to just see what you have seen, like that, like what you have talked about. So yeah, okay. So fine. So yeah, there are three possible cases. So the last one, that is basically when the Riemann surface is basically conformally equivalent to D. So in this case, there are not much variation. So there are only two possible cases. So I'll talk in a minute, or maybe in some situation when it arrives. But yeah, so mostly we will be dealing with these two cases when it is in a C hat or C. So we'll be taking the functions from C to C, or A from C hat to C hat. Because in this case, the extreme challenging situation can be arrived. So these are like very much wild in nature. So if we take any function and keep on iterating these things, so this is not very easy to handle. Okay, so let me tell you, like so the initiation of this method, like why we are talking about this iteration. So it started in 1870 by Schroeder. So he took the method called Newton's method of finding a root of a polynomial. The scheme is, as we all know, that this is Zn plus 1 equals to Zn minus f of Zn by f dash Zn. So that is Newton's method for finding the root of a polynomial. So Schroeder did the same thing, and he just applied, say, this is a function, new function, say nz. This is z minus fz by f dash z, and he keeps on iterating this function n, basically. So n square, n cube. So this iterating means this composition with itself n times, and n goes to n. Okay. So what happens is that, so if we see, say we choose an initial case, say z naught, and we keep on iterating this point. So if the initial guess is like sufficiently appropriate, then that under so under this function, this basically goes or converges to the root of the polynomial. But here we have to be very much precise, because if we do not choose the point in a sufficient like in a sufficient proximity, then that point cannot, like, may not be converged to a root. So maybe I'll illustrate these things by taking this example, say fz goes to z cube minus 1, and we all know there are like three roots. So okay, so maybe I'll insert a picture which will give a better understanding. Yeah. So yeah, as you all can see that the here is a root. So here is a root, and here is a root. Here are basically three roots, and if we start choosing this point as z naught and keep iterating, after some time it will converges to this root. Or even if we start from this point, it will come here, come here, come here, maybe it will come here, then here, and then it will converge to this root. So basically this set was the purpose of studying that if we choose any point, whether that point converges to the root of the polynomial or not. So this idea basically generalized by letter Fatou and Julia for like in a global sense. So in that case, we can choose this point at any position in the complex plane. Okay, so let me say something here that the points which are converging to the roots of a are basically the set of points which are converging to the root of this polynomial are stable. Means if you take any 2 points nearby that point, then that point, say this is one more point here, which is like small like vicinity of this point, then this point will also converge to this root. So that is why this kind of set of points is basically stable, and the boundary of this set means this set is basically chaotic. Chaotic means if you choose any point from the boundary of this set, then that point will never converge to it. Okay, so started with this. So we'll keep on doing this in a global sense, not in a local sense, because in this case, if we choose a point in a sufficiently small vicinity of that initial guess, then this method converges. Okay. So now, okay. So this was done by Fatou and Julian in 1920, and later it was extended by Baker. So, okay. So Fatou and Julia, they initially started with rational maps, and later Baker extended this iteration theory for transcendental integer maps. Okay, so let us okay. Let us take a rational map F from C hat to C hat. Okay, so let me tell you one thing. Like, it is known to everyone that any analytic map from C hat to C hat is nothing but irrational. So rational maps are the only analytic. Okay. From C hat to C. So that is why first of all we'll talk with these rational maps, and later we'll move on for the transcendental intervals. So if you take any rational map from C to C hat, then let us see what happens. Okay, so once we are in C hat, so we will talk or we will deal with the spherical metric. Okay, so because since we'll be talking about the distance between 2 points, between 2 iterative images, then we need a metric. So that metric is basically spherical metric. Okay, now first of all, let us start with some simple examples. Take fz to be okay. So is the meeting going on? I don't know. Like, is it paused or hello? Hello?
Yes, Agnivar.
Right,
Oh,
and the
sorry.
screen is not visible.
Okay, okay.
Screen is not visible.
Okay. Yeah, now it is fine.
Yeah.
Okay. Okay, so first of all, let us start with some examples. Say fz equals to z plus z plus a, where a is non-zero. Then we can see that infinity is the only fixed point of this function. Okay, so now if you just keep on iterating this point, take any point, like any point z naught in c hat, you keep on iterating this point. So this point will converge to infinity irrespective of z naught, like what you choose as n goes to infinity. So if you take, say, fz equals to az, this is basically a scale notation. Then, like, there are two fixed points, is 0 and infinity. And in this case, if you just keep on iterating the points, then fn0 will be going to 0, and fn infinity, this will be also infinity, and fn, say, z naught is basically an z naught for all n belongs to natural number. So this is natural number. Okay. So now see what happens. Okay. So okay. So here let me use the notation. So these points z naught, if z naught, if to z naught. So this set of points, if we take the set of points, this is called the forward orbit of the point. Okay. Then for this point z naught, what happens is that O plus z naught. So I want to know what happens for this point. So to find like what is the forward orbit of this point. So in this case, like there are three possible cases. If your modulus of A is strictly less than 1, you see that your orbit will go to 0. If your modulus of A is strictly greater than 1, your orbit is going to infinity. And if modulus of A is equals to 1, then your orbit basically lies in a circle. So yeah, in this circle. So here we have also two cases. So when A can be written as 2 pi I theta, where theta is rational, then in this case, the iteration basically converges to a point z naught. And in this case, I'll come in a minute that this iterate that the point where the iteration converges is basically a fixed point. And if A is not in this form, that is A equals to the power 2 pi I theta, where theta is r minus q, then this process never converges. Basically, this does not converge to any point. Okay, it never converges. Okay, so from here it is easy to see that if a sequence, if this sequence z of say z naught converges to some point say L, then this L must be fixed point of F. So this is very like easy. You can see that L, say we start with this limit n goes to this, and yeah, since the like due to the continuity, you can simply write this, and this is f of L. So this L becomes a fixed point of this function. Okay. So now, so the question is, what are the conformal maps from C hat to C hat? What are the conformal maps? So we all know that these maps are nothing but the Mobius maps, that is Az plus B by Cz plus D. radian minus bc is non-zero. So then what happens for this case? So I'm starting with the simple examples, but later you will see that how complicated is this. So even for a map of of a map, like simple map for a quadratic map or cubic map, so that the situation is very much complicated. Okay, so for this, okay, maybe for the to maintain the time, maybe I'll keep it as an exercise that if you take any map, like Mobius map of this form, then one can show that if, okay, so there are at most two fixed points for this Mobius map. So if has so that single fixed point may be repeated, it doesn't matter. So say zeta, obviously obviously we are taking we are not taking the trivial case that zeta is infinity. So obviously zeta is not infinity, so that case can be handled in an easy way. Okay, so then if in z goes to zeta for all z in c, so that is like very much easy to just check. And second, if has exactly two fixed points, say zeta 1 and zeta 2, and they are obviously distinct. Obviously, zeta 1 is not equal to zeta 2. Then either f and z converges to one of the fixed points, or the iterated images forming dense subset of some circle. Okay, so these things are like very these are not difficult to check. Okay, so okay, so now let us come to this definition, because this is the main key definition by which all the theory will be developed. So this is called equicontinuity, and later we'll see that some results are also there which are equivalent to this. Okay, so suppose you are taking a family of functions Ph.D. So say this is the collection of maps from say D to C, where D is a subset of C, and we'll say, and to take Z naught be a point of D, we'll say that this sequence of this family of functions is equicontinuous at this point Z naught if for any epsilon greater than 0, there exists delta greater than 0, such that for all Z in D and F in script F, this distance of f z naught from xz is less than epsilon whenever this distance of z from z naught is less than delta. So here, yeah, so here we can also talk about the caudal metric, because this caudal metric is also like equivalent to the spherical metric. Okay, so what is the purpose of taking this definition, equicontinuity? So these are some nice purposes. So the equicontinuity is basically this is basically the idea of the preservation of proximity. So it means if you take any point z naught and you just look at whether the sequence of like family of functions is equicontinuous at that point or not, you will obviously get some other points surrounding that point. At those points, the function will be also equicontinuous. Means there exists a maximal open subset of D on which this family is equicontinuous. So this is the purpose. So that is why this basically helps us to take care of those points which are basically stabilizes or converges to a fixed point. So by this definition, we will define what is a Fatou set. So Fatou set is the collection. This is the collection of those points in C hat such that, okay, so as I have used this notation F, so I'll use it throughout this talk. So this family, because here basically we are interested for the iteration of functions F. We started with C from C F to C hat, and we want to know what happens for F, F2, F3, F4, and so on. So that is why I have taken Fn. So this family of functions is equicontinuous. So these are the collection of all these points. So that is, as we have seen, that for any point we will have a neighborhood for which the equicontinuity will be maintained. So that is by this definition, this Fatou set is open set. And the Julia set is the complement.
Sukanta.
Yeah.
Actually, I have a doubt. Since you have defined
Yes.
like set, so you are saying this sequence of iterate is equicontinuous on, I think, neighborhood of Z.
This equicontinuous in some neighborhood of the, yes.
Yes, because it will be well defined something in the neighborhood now.
Yes, obviously, because
I
here I have mentioned.
If I say quite precise, so I think for every compact set of the neighborhood of Z.
So I'm coming to that point. So first of all, I have just given this definition by equicontinuity. I'll be giving an alternative definition again. Okay. Yeah. Thanks, Gaurav. Yeah, Gaurav, thank you. Okay. So the complement of the Fatou set is the Julia set. So in Fatou set, it is the collection of those points which are basically behaving in a similar manner. It means if you take 2 points nearby and keep on iterating these points, those 2 points will be the iterated images will also be nearby. Okay, so yeah, so let us now give me. Okay, so as I have given this definition, so let me give one more definition, and then I'll come back to an alternative definition for Fatou set. So now I'll say something about conjugacy. Okay, conjugacy. Say two rational maps, say R and S, are said to be conformally conjugate if there exists a phi Mobius map. This is basically Mobius, such that suppose you can write anything. Okay, so phi y inverse S equals to phi of phi inverse. Okay, so what happens for this thing? This is basically, okay, since we have taken this conformal map phi, so it is a like biholomorphic function, because if phi is conformal, phi inverse is also conformal, so biholomorphic. So that is basically that biholomorphic function basically preserves the equicontinuity. So that is why I have first mentioned equicontinuity here. Okay, let me write here. Equicontinuity. So what is this? So it means this is one, then Okay, so let me denote this Fatou set. Denote this Fatou set by script f. This is the usual notation, and the Julia set is the script j. So these are the notations by which I will denote the Fatou set and Julia set. Okay, so in this case, if one holds, then the Fatou set of S is nothing but the phi image of the Fatou set of R, and similarly the Julia set of S will be same as the basically phi image of Julia set of R. So what it actually does, it does basically it keeps the equicontinuity preserved. So that is why we don't have to bother about if S is equicontinuous. Like sorry, if S is if the map S is normal in some domain, whether R will be normal or not. Sorry, not normal. I have not come here. Equicontinuous. Yeah. So the purpose of this conjugacy is that if S is equicontinuous, not S, basically Sn is equicontinuous, then say in some domain D, then we can talk about the equicontinuity of R and vice versa. So by this we can completely know the Fatou and Julia set of two maps if one of them is known to us. So sometimes what happens, say we have two maps S and R, we know the Fatou set of S, but we are in search of the Fatou set of R. So in that case, for R it is not easy to find out. So first of all, we will find it for S, and then we will come back for R via the map phi. So this is the purpose of taking this conjugation. Okay, so I will do this. Okay, now I'm coming to the alternative definition as both of you have suggested that. Yeah. So this is due to as the next one. So the definition of normality. Say we have a family of functions defined on a domain D to C hat, and obviously D is subset of C hat. This is this family of maps is said to be normal in D if for every sequence of script f there exists a subsequence of that chosen sequence such that not such that. So if you take any sequence, so then that sequence will have a subsequence converges uniformly on every compact subsets of D. So this is basically a local behavior. That means if you take any point from, say, if you take any point from D, so you can find a neighborhood, say in Z0, which contains Z0, we will obviously find a neighborhood. So in that neighborhood, this kind of property will be happening. So this is not a global property. Okay, so and this is always equivalent to saying that that if the family of functions is local uniformly bounded on every compact subsets of D. So basically, these are the equivalent definitions. So I'm not going in the proof of these equivalent definitions. So all these things can be like seem to be like understandable, I think. Okay. Now, okay. So let us see an example first. Take fz equals to z square. So it is easy to see that if you take any point whose modulus is less than 1 and keep on iterating this point, this will go to 0 as your n goes to infinity. And if your mod z is greater than 1, you keep on iterating this thing, will go to infinity as n goes to infinity. Further, for any point z not in the unit disk, so this is the unit disk, so this is D. There exists a R greater than 0. Obviously, R is less. Obviously, let me correct this in this one. 0 less than or less than 1, and such that modulus of this circle, that is z such that mod z minus mod z0 less than r. And obviously, like we have to choose this r like sufficiently small so that it do not like it does not exceed our disk. So okay, let us put this inequality. This is a closed ball. So if you take any point z, you'll have some neighborhood of this point, basically closed neighborhood, where this family of functions is normal, basically. So, but note that this family of functions fn is not normal in mod z less than 1. So if you take this step that you need this to be the whole domain, then in this whole domain, the sequence of function, okay, not normal. Okay, so this is a mistake. This is not uniformly convergent. So that is why I'm saying, okay, let me write here. This is if you take the iteration of z, this will be z to the power 2 to the power n. So if you take this domain, then in this domain, the sequence of function is not uniformly convergent, but it is actually, if you take any point and take a closed neighborhood of that point, then there the uniform convergence of that sequence of function will happen. So that is why I am saying this is a local property. Okay, so and similarly also, if you take any point, like outside the ball, take any point outside the ball, say z0, and same in the same way, you can see that there will be some neighborhood of that ball where the sequence of functions is basically uniformly convergent, and that limit function is in that case is infinity. Yes. So that means what we get is that this D and C minus D closure are in the Fatou set of F. So what happens if you take any point on the circle mod z equals to 1? So let us decide what happens in this case. So if you take any point z0 from the circle D, okay, let me write. then you can easily just check that this sequence of functions fn will never converge uniformly. So that means in that case that set of points z such that mod z equals to 1, this is basically unit circle, this one is the Julia set of the function. So for this function, we have found out that this inner part and the outer part, these are in the Fatou set, and the boundary of this unit disk, that is the unit circle, is in the Julia set. So this is like not very difficult to check. It's very easy. But this becomes very complicated if you just change the function by some sort of like scalar. Okay. So that is why this definition is not always good to handle with. So later in 1926, Montel came with this criteria by which we can just easily check whether a sequence of function is normal in some domain or not. So this is called fundamental normality test. Which says that suppose you have a family of functions, obviously, as I have earlier mentioned, this is like analytic maps. If you have family of functions, say this is and say the domain is D. Okay, so let me precise this. And let this omega be a set which is basically c hat minus union f belongs to script fd if this set omega omits at least 3 points, then the sequence of function or not sequence of function because here it is in general any family, then this family of functions is normal in D. So now just go back to this example. Okay, now you see for this function f z equal to z square, if we take the unit ball like open unit disk and in every iteration the all the points remain inside the unit disk. So that means if you just take the union of this, so we will get that c hat minus disk for z in disk. So this will be the set omega, and this clearly omits at least 3 points in c hat for the function f z equal to z square. So that means this set D that open unit disk is basically is in the set D the function f is normal. And similarly for the exterior also you can just put these things here and just check. So this is the way, and this breakthrough gives several results after that, like made by Fatou and Julien. So those properties I will be discussing in some other lectures. So here I'll be mentioning few more things. Okay, so okay, now let me give one more example. Then you can understand like how it's not always easy. Okay, simply you just check for this function. So simply this is a quadratic polynomial and it seems to be like easy to handle. But if you just iterate, and you can see that this becomes very much difficult. So there are some sort of tools by, or you can say techniques by which we can handle some functions, but there is no method, like well-known method, like which will apply, or which can be applied for all the maps. So for this, like our main purpose is to find what are the stable points and what are the chaotic points, or indeed what is the Fatou and Julia set in particular. Fatou set of F and Julia set of F. So we have to find this. Okay, so let us start with this polynomial Pz. So say this is z square. Okay, now I will and take this uz to be z plus 1 by z. Now consider this diagram. Okay, first of all, yes. So means if you take z from this interval minus 2 to and take phi of not phi, this is q of z, then q of z, this will be lying in a unit circle. This is basically S1. So this is my interval minus 2 to 2. Yeah, so this is no. I have written. Okay, so this is, first of all, let me do this diagram, then I'll say this is my P, this is my Q, and this is my F. So if you take any point Z from the unit circle, so this is my unit circle, this is mod Z equals to 1, then Q of Z takes this point to be in minus 2 to 2, or in this, or precisely you can say Q of S1 is precisely minus 2 to 2. Now you can see this diagram. So I can write that if to be Q P Q inverse, but here I need to be very much precise, because Q is not, my Q is not an not a conformal map. So I will take the like sufficient, like a suitable branch for Q. So yeah, and now see, take any point Z from C hat minus 2 to. So I think this diagram is well understandable. So means if you take any point from this interval minus 2 to 2 under this Q inverse is it is going to this circle, and then under P the circle remains itself, and then under Q also it comes back to this interval minus 2 to 2. So now if you take any point Z from this C hat minus 2 2, then see what happens. Let's see what happens. Okay. So in that case, you can simply take can calculate this. Note that Pn of Q inverse Z is going to infinity for Z in C hat minus 2. So therefore, if Pn Q inverse Z goes to infinity, then under Q, this also goes to infinity. That means if n Z goes to infinity, as n goes to infinity for all Z in C hat minus 2. That means we have this family of functions is like uniformly convergent for the points outside this interval -2, 2. So that means the Fatou set, that this set C hat -2, 2 lies in the Fatou set of F. Also, the Julia set lies in the interval -2, 2. But now it is important to check, is there any point? Is there any point Z in this interval which lies in the Fatou set of F? This is the question. So if I do this, then this characterization will be completed. Okay. So now see carefully. Okay. See that if I take any point from this interval, it goes to this point. Under P, it goes to this point. Then under Q, it comes back to this some sort of this point. But if I take any point which is not in the interval -2, 2, suppose, yeah, here, is it visible? Here, then that point is basically going to infinity as I have shown here. So that means I am having two ideas. And as I have said, if there is any point in the interval which is in the Fatou set, so that point will have a neighborhood, and that neighborhood will be also in the Fatou set. So what is actually happening is that so under Fn, if you take any point from here, it remains here. But if you take any point from the outside of this interval, then under Fn, these points goes to infinity. So that is why if you take any neighborhood of this point, there will be always some point for which this family of functions is not normal. So that is why there is no such point in -2, 2, which lies in the Fatou set of F. Therefore, precisely we have that the Julia set of this map is precisely -2, 2, and the Fatou set of this map is basically C hat -2, 2. So this is precise. So one good generalization of this understanding can be this. So let me write this. So I'll appreciate if someone does this. Okay, so the exercise is that for any two given points Z1, Z2 in C hat, obviously Z1 is not equal to Z2. Does there exist a polynomial whose Julia set is precisely the line segment joining Z1 and Z2 and containing these 2 points. So I think this is understandable. Suppose you have this plane, you have taken any 2 points Z1 and Z2, you just join them by a straight line. So my question is, does there exist any polynomial whose Julia set will be precisely this line segment? So I think one can do this, and maybe I'll write the answer. This is basically this answer is yes, one can do this. So for any kind such 2 points, there is some polynomial for which this happens. So one can just, if he is interested, he can explore this. Okay. So I think, so can I take 5 minutes more?
Yes, sure.
Okay. So okay. So within these 5 minutes, I will say something, some sort of definitions about these Fatou sets, and then I'll stop, because after this, like after this, after this talk, we'll need this kind of these definitions. Okay. So as I have earlier mentioned, the forward orbit. Let me define the backward orbit. So backward orbit of a point W under F is the collection of those points in C hat such that F n Z equals to W for some n. So that means the backward orbit is basically, so we have say W here, and we take the preimages under F, say it has 2 preimages initially, W1 and W2, and then you take again preimages, then you take again preimages, and keep on doing this. So this set is basically the backward orbit of this pointer. And now I'll say just one more definition. Simple definition that is called completely invariant. Suppose we have a Fatou component, say U. U is a Fatou component. We'll say that this is completely invariant if of U, subset of U, and if inverse of U, it is again subset of U. So this is called forward invariant. This is called backward invariant. So if these two happen simultaneously, then we'll say completely invariant. So for this example, earlier example, f z equals to z square, we have seen there are 2 completely invariant Fatou components. One is the interior. So this is completely invariant Fatou component, and also the exterior. And this exterior is also completely invariant Fatou components. So there are 2 completely invariant Fatou components. So I think this is a nice position to say something about this completely invariant Fatou component, that there is a conjecture that okay, maybe I'll talk in a different lecture, because that insists of transcendental function. Okay, let me okay. So, after this, okay. So there are types of Fatou components. So what are the possible types of Fatou components? Okay, maybe I'll speak about this in the next talk, but before that, I'll use some to demonstrate that it is very much complicated. Okay, I think it's visible. So see that. So this thing I'll talk in the next lecture. So see that in this picture. So here the function is fz equals to z square minus 1. As you can see that the black region, there are like 2 regions, black region and blue region. So the black region is the interior part, which looks similar to that function fz equal to z square. So the black region is the Fatou set, and similarly the blue region is also the Fatou set. So if you take any point from this black region, it converges to some fixed point, and if you take some point from this blue region, it converges to infinity. But you see the boundary. So if I zoom this, if you see the boundary of the set, it is like very much chaotic. in nature. So that in this case, the Julia set forms a fractal structure. And indeed, in this case, the Julia set is basically the like it is the union of infinitely many closed curves. And the interior of these closed curves are basically the Fatou components. Okay, so maybe one more feature will give different kind of shapes, maybe this. Yeah. Yeah, I think you can see this also. So now look at this function. So this is fz equals to z square plus I. This is just C. We are just dealing with just quadratic functions. So it is that much like wild in nature. So if you zoom on this structure, if you see this white part, so this is a connected set, even path connected, compact, but uh, but yeah, it is also locally connected, and it is the precisely the Julia set of this function. So the Julia set of this function is this kind of set, which is called dendrite. And see the wild behavior of the Julia set. So here also the Julia set like is not like very easy to like handle. Okay, next one will be this one. Okay, so this example. So this example also okay, there it's some okay. So here the function is so yeah, the function is very much precise. This is 0.99 plus 0.14 I. So this is the function. For this, the black region is in the Fatou set, blue region is it is also in the Fatou set, and the boundary is the Julia set, and the Julia set is in this case is a simple closed curve. Although it is looking like that Julia set will be like some it is union of something, but it is indeed a simple closed curve. So there are some softwares by which I have generated these pictures. These are uh, like not easy to just handle. So that is why I have just used this software. And maybe this is the last example. I'll not take much time, just to illustrate that what kind of wildness can happen for Julia sets. And this one. So this is also one function, which is the function is z square minus 0.765 plus 0.12i. But here the thing is something different. You see some sort of discreteness, or you can say disconnectedness of the boundary of the set, right? So here the Julia set is not connected as we have seen for the earlier cases. So in this case, the Julia set is a Cantor set. So there are many possibilities of the Julia set. So I have just explained with these few examples to understand what are the possibilities. But yeah, there are many possibilities. So I think these introduction will be helpful for the next consecutive talks. And yeah, if you have any questions, you can ask. Yeah, and I think I'll stop here. Yeah.
Hello. Do we have any questions? Anyone? Okay, so like I have one question, Sukanta.
Yes.
Yeah, so like the examples you gave, I can see that these examples contains like the last one is I think the Julia set is totally disconnected and upper.
Yes.
The previous examples
Correct.
are connected and locally connected Julia set.
Correct.
Yeah, so uh, my question is like and examples are z square plus c in the form of z square plus c.
Okay.
Isn't it like here it is z square plus something, here it is z square.
True.
Yeah, so c is a c is in some c is some complex
Yes.
number. So like for which values of c like Julia set is locally connected? Is there any characterization known?
Not locally connected, it is not precisely known, but for connectedness, it is known. This is called the Mandelbrot set. So you will collect
sorry,
those.
what?
Like Mandelbrot set. You're talking with this parameter c.
Yeah, so I'm saying that
So if we,
yeah. So for what values of c like the Julia set would be connected? Like, is there any characterization
yeah.
for c is known?
Yes. There are some characterizations. This is called like the Mandelbrot set. This is basically the collection of those C in C such that the Julia set is connected. This is called the well-known Mandelbrot set. So I think I also have this
Connected.
picture maybe. Yeah. So let me just show you. Mandelbrot set. No, I didn't have it. Yeah. So
Okay,
yeah,
so like
but yeah, true. But
yeah, does connectedness here implies locally connected?
No. There is no
So,
connection with connectivity, like connectedness with locally connectedness and vice versa. There is no connection.
so I'm saying that in this case, like z square plus c, does there exist a Julia set which is connected but not locally connected, or vice versa? Does there exist?
Okay, connected but not locally connected. I think there are, but yeah, I have to be very much precise of the form of this function. I think, but I am not like I cannot give you right now the precise example like this.
No. This is actually totally disconnected. So there is no point of
Yes.
connectivity. So,
I understand
okay.
your question.
Yeah.
So I have to be very much precise when I am constructing the function. So yeah.
Okay. Maybe
So
I will
I
ask
think
you
there are
later.
some examples. Yeah, I have to look at those.
Okay.
Mhm.
Yeah, I would be interesting to see that one.
Yes, definitely.
Okay. Any other question? Okay, if not, then let us thank our speaker. So, Sukanta, thank you.
Okay, thank you.